Okay, so let's start today's class. So hopefully everybody submitted assignment 4 yesterday. Okay. So have you graded assignment 3 already?
No.
Okay. So, but you will in a few days, right?
Near the end of week.
Okay. So you'll get the assignment 3 grading pretty soon, in about 3-4 days. So somebody said, maybe we won't get the feedback for assignment 4 before the exam. So I'm going to spend a few minutes trying to discuss assignment 4, which you've just submitted. So hopefully you remember some of the details of the assignment. So 4 problems. I think this third, let me start with the third problem in non-linear way. So Gibbs sampling. So how many of you got confused with this question? I know you did. So even before Gibbs sampling, you need to kind of recognize that this is just a distribution of a mixture of 10 Gaussians. Okay, 10 is arbitrary. You could have just chosen 2 Gaussians, let's say. So it's a mixture of 2 Gaussians. That's the distribution there. Okay. So if you have a distribution of 2, or let's say 10 Gaussians, how do you sample from a mixture of 10 Gaussians? Okay. Forget about Gibbs sampling. Any sampling. Give me any sampling strategy to sample from this mixture of 10 Gaussians. And one way to do it is to actually think of a generative process, where in the first step you pick one of the Gaussian components, and in the next step you sample from that Gaussian, whichever Gaussian you picked in the first step. Okay, so that's the generative description of a Gaussian mixture model, which means in this case you'll pick one of the components with probability lambda k. So you'll pick the kth component with probability lambda k, first component with probability lambda 1, last component with probability lambda 10, right? So that's a categorical distribution or a multinomial distribution, roughly the same thing. And then you pick one of the components, maybe it's the 6th component. Then you just sample a number from the 6th component. 6th component is a Gaussian with mean being square root of 6 and variance being 0.01 times 6 square, right? So is that just sampling from a mixture of Gaussians clear? Anybody has a issue with that? Then we can now talk about Gibbs sampling. So let's see. So for Gibbs sampling, I was mentioning, so many of you have already done this. So what was the starting point? Any of you?
Taking sample from DNM and I was not able to do Gibbs sampling. So I did.
But you were able to sample from the mixture of Gaussians at least. So if you draw the histogram, this is a one-dimensional thing, right? Pi of x was sum up to 10 of lambda k of normal with some mean and variance, right? Whatever, depends on k. But so you were able to at least draw these samples and estimate the mean and mean of the first 500 and the next 5,000, something like that. Yeah.
So it becomes a binomial distribution, right? Of x and lambda. So we first sample x from given lambda.
Yeah.
And then in the next equation, given the lambda to point, we again sample the x and we do iteratively circulate the Gibbs function.
Yeah. So just to repeat what Ronak said, so you think of a joint distribution. So pi of x, to think of a joint distribution, so instead of pi, let me just call it p of x, just to be very clear. P of x is equal to little x is this probability, right? For every little x value, so there's this n function, which is basically 1 by, if you remember, it's just 1 by square root 2 pi sigma k e to the power minus x minus mu k square divided by 2 sigma k square, I guess. Yeah. So that's the function, right? So you have a sum of k such functions, 10 such functions, right? So finally, p of x has some form, some complicated, it's just not complicated, it's just a sum of bunch of exponential terms, that's all. So some function. Now, one way to do it, and this is not probably the only way, is to think of a joint distribution between k and z, okay, where now I've introduced a new random variable k, okay. So what is this random variable going to be? It's going to be the same intuition that we had. K is going to somehow represent which component did the Gaussian come from, and x will be the value from that component, okay. So that's the joint distribution. So I introduced a new random variable k, and now, I know joint distribution can be factorized in any way, so I'm going to factorize it in a way which is kind of, I'm going to factorize it in a particular way. So let me just write it down very explicitly. So p of k is equal to little k, and x is equal to little x. This p of x is equal to little x, given k is equal to little k, times p of k is equal to little k, right? This is a factorization of two random variables, right? Now, I'm just saying that k is a random variable in the generative process, which is just picking which component the x comes from. The current sample, for example, little x comes from. So p of capital K is equal to little k is just lambda k. Okay, lambda little k. And this one, so given a component, probability of x taking little x is just pick that Gaussian, and you exactly have that. This is actually just by the same thing, that formula that I wrote above. In fact, this is actually equal to this. Okay. Condition on the kth component, you will only get a sample from the kth component. So you know that the kth component is just a Gaussian with some mean and some variance. Okay. Okay. So why did I introduce this joint distribution? Is so this joint distribution view, if you actually now come back to what is p of x is equal to x, which was written above, this has to hold sum over all the values that k takes of p of x is equal to little x and k is equal to little k. Okay. What are all the values that little k can take? Okay. This is just p of x is equal to x. This is just marginalization, right? I'm kind of trying to get rid of one of the random variables. So I kind of sum over all the values that it can take. What are all the values that it can take? Little k can take a value. So actually, since it's categorical, right? So categorical, this is a short form for writing a categorical distribution. If you think of a multinomial, a multinomial distribution is what? It's saying in 100 trials, what is the probability of coming up with the first component some number of times, for second component some number of times, third component some number of times. Okay, it's just a generalization of binomial. Binomial is saying in 100 trials, how many times do I get heads, how many times do I get tails. Okay, categorical is just saying in one trial, which of these, in this case k or 10 observations, which of these 10 components would realize. Okay, so anyway, so because joint distribution splits like this, and I'm gonna do a summation. Okay, you can see that if I do a summation over all the values k takes of the joint distribution, you can see that this is actually just lambda k, and this is the same thing as this, right? So this was the object that we've been given. This is the object that we've been given. I'm just saying that thinking of this latent variable capital K does us no harm. And now you have two random variables. And now you know how to work with two random variables, right? So k and x are the two random variables. So if you just concatenate them, it's a two-dimensional vector, right? So you want to get little k1, little x1, little k2, x2, and so on. So this is what you would get via Gibbs sampling, and you can ignore the first coordinates. Okay. How do you get this? So, for example, going from here to here is what I'll describe. This requires two conditional probabilities. Probability of x is equal to x given k is equal to k1, because that's the previous value, right? From here I can draw a new guy, which is going to be, let's say, x2. And then to draw k2, I can do probability of k is equal to something given x is equal to x2. Okay. Right. In this, so let's say I have one sample. One sample means just one example. I have both the numbers, which component and some number. Okay, let's say we have it. You can always start with some arbitrary number. Question is next. You remember gift sampling was basically just dependent on the previous example only. In the previous example, I know both the coordinates. Let me start with getting one coordinate at a time now. I just picked getting x2 first. I mean the second coordinate first. You can always start on this side as well. But so the second coordinate, to get the second coordinate, I'll have a conditional distribution. It's the conditional probability of the second coordinate's random variable. I just need this conditional probability, the generic thing, which is a function of x. X is generic argument here. Given the coordinate, the other coordinate value I don't know, so I'll take it from the previous sample. Okay. So let's say from this conditional distribution we know what it is. This is just a Gaussian. If I know the component, this is just one of the. If it is k1, then just take the k1th Gaussian, just get a sample. That will be this x2. And now I know x2. So given x2, I need to know how to sample the k2 component. So this is the part where you have to do a little bit of computation. Okay. But this is not difficult. You already know the joint distribution. You know the joint distribution. So given a joint distribution, finding a conditional is not difficult. Okay. So that is in fact the strength of strength of gift sampling is saying is actually more subtle than that. Given a joint distribution, finding a conditional of this form where there is only one component on the left side is relatively easy. That's so you say, okay, we want to get a sample from this computed joint distribution, but if you are asking us to compute from here to here, that may be hard. But the nice thing about gift sampling is, given any joint distribution, finding at least one, this type of conditional is relatively easy. So that's one of the key things. And this thing, this is going to be some other categorical distribution, because k is anyway takes only 10 values, 1 to 10. So there is some PMF here. Just get a sample k2, and so you fill this row. Now go to the next one, and so on. That's the gift sampling.
X1, X1 are arbitrary.
You start from somewhere, so yeah, you can choose something. Doesn't matter. Yeah.
How will we make sure that we are the burning of time?
Yeah.
Starting from whenever we are reaching the top of the PDF. So how will we?
We are not reaching the top of the PDF.
Like we were taking sample from the area around higher region of PDF, right?
Our goal is to get a sample from this P of x. Our goal is to get samples from P of x. So, but we are doing it in this way. But ultimately, whatever x's that we get, they are as if we are getting it from here. Okay. It's not the case here, right? Because you're sampling from conditional probabilities. You're not sampling directly from here. Okay. So the burn-in stuff that you kind of alluded to is just saying that, okay, so this corresponds to a transition probability object Q. Remember in the notes. So this transition probability object Q that corresponds to these two steps has a stationary distribution P of x by design. Okay, by design because not P of x. In this case, it's two coordinates, the P of x comma z, so k comma x. By design, this is a stationary distribution of this transition probability object. Okay. The question is, so stationary distribution has a specific meaning, right? So if you keep sampling from this transition probability object again and again and again, going from one sample to one sample to one sample and so on, you will see that most of the samples will come from, if you draw the histogram, they will come from this. Okay? The histogram will be very similar to as if I got the samples from here. Okay. Now, how long is the question? So initially it will not be the case. Initially for some number of some number of operations on this. So the transition probability, with transition probability you go from one sample to another sample to another sample. initial few samples will not resemble as if they are drawn from the stationary distribution, but after some time, which is a burn-in, you will see that the samples the histogram resembles the histogram you could get from directly from this. That's burn-in.
It's like we don't have to do anything for that. Like if you were to
No, I mean, if you knew what the burn-in period was, like at what point, you basically the problem in Markosian Monte Carlo is that the initial few samples will not be good samples, okay? Because after a long enough time, the samples will be as if they are drawn from stationary distribution. That was the property. So you don't know at what time you have to start believing your data, and at what point you want to discard. That's the issue.
we are not taking any acceptance probability.
Acceptance probability. No, there's a particular transition probability object or matrix or kernel, whatever you want to call it. Acceptance rejection comes in a different Monte Carlo technique, different Markov chain technique. That's a slightly different Markov chain technique. The metropolis hasting one, that's there in the other question, right?
What I thought is like having acceptance probability, because of that we can reject the samples and which are at the tail side of the distribution, and we can accept the sample who has higher probability in the distribution.
No, that's not the idea of acceptance. Acceptance is saying you want to sample from some p of x, but you're actually sampling from q of x. So therefore, there's a mismatch, right? You want to get from p of x, but you're getting from q of x. So some samples you probably want to discard. Okay, that's the notion of rejection sampling, and also notion in key kind of concept in metropolis hasting. Okay, it's not about if you want to sample from p of x, you're not focusing on the high peak region of p of x and the tails of p of x or anything like that. Okay, acceptance is something else slightly. Okay, so that was that question. Now, number 2. Any issues with number 2? I mean, the algorithm is laid out. Okay.
I think the alpha defining custom reactions and all of that.
Fine.
I mean, should we switch that? Because I remember in the lecture it was like the pi.
Is that inverse of this?
Yeah, inverse. And as well as the function of the normal distribution function.
This you can choose anything. I mean.
Yeah, but I mean it needs it doesn't have to right.
Oh yeah, that's true. Yeah, there's no 2 here. This I'm not sure. Manas can cross check. Or you can take it in PVD or something. So basically, if it is symmetric, right? I mean, this is a symmetric function of x prime and x. Okay. If it is symmetric, then g of x prime given x is the same as g of x comma x given x prime. So basically, you get rid of this. Okay, the numerator and denominator cancel. And so this actually. So I mean I think that has a special name. I forget. I mean, if you use symmetric this transition property thing, then you have a special name. But yeah. So anyway, so what was your question?
It should be reversed. Like x dash is the next sample we gonna.
Pi of x prime should be the numerator.
Pi of x dash, yeah, by x prime.
Okay.
Anyway,
Okay.
gonna get cancelled.
Then why didn't you point it out in the Slack channel or something?
Anyway, it's gonna cancel out because it's just so.
No, why would pi of x?
The other thing.
Pi of x and pi of x prime will not cancel out. So you are actually doing something incorrect if you follow this. But let's see. I mean, it's okay. I mean, but the flavor of the algorithm is the same. I mean, you draw a sample given. So if you assume this to be Gaussian, you draw a sample from the Gaussian, compare functions of that number with the previous number, and get some alpha. And if alpha is with some probability alpha, again, with probability alpha just means you flip a coin with that alpha probability. If it lands heads, then you accept x prime. If it lands tails, you regenerate some other x prime and go forward. That's metropolis hasting. So, what is it? No, I mean, so the reason why there's a min of 1 comma something is this can be either greater or less than 1.
Yeah, but if it is wrong, like if it is phi of x prime upon phi of x,
Yeah.
then it will be higher.
Always greater than 1, that's not true. That's not true. No, that's not true. Otherwise, there would not be any need for min and all that. Yeah. I mean, alpha is positive number that's given because all these things are positive. Phi is positive, these are positive. It's just that alpha has to be also upper bound number 1 because you are actually sampling with alpha. So, I mean, in a sense, the Bernoulli parameter can only be between 0 and 1, right? Okay, but I mean, for this you already know what the answer should be. I mean, you can actually compute it and know, or you can directly forget about metabolic slicing. You can just sample from randomly from the Gaussian and then just compute this doing a Monte Carlo average, right? So you should be able to see that the answers are similar. Okay. First question. Any issues with this one? Any issues with this one? So this is actually the assumption made in many ways. The first assumption, which is birds are conditionally independent of each other given one. So probability of is this. So how did you guys divide the task? It looks like some of you have not seen these questions. Some of you have never seen these questions, and some of you have seen it. Okay. So all I'm saying is probability of, let's say, x1 to, I don't know what the. Oh, this is not the one. X1 to xd given y is just the product of little d is equal to 1 to capital D of probability of x little d given y. Okay. This is the naive Bayes assumption. That's all. So, oh, not this one. So the joint distribution of all the random variables, you can always factorize it and factorize it in a nice way such that you get the product form. Okay. Which is just a fact. Take the first term to be so p of all the guys x1 to xd comma y. Just think of it as this p of x1 to xd given y times p of y, and this part is just that. Okay, that's the answer to the first part. And now we are asking what is the probability of y equal to 1 given x. So this is just Bayes rule, application of Bayes rule. Okay. So people should be comfortable applying Bayes rule for, let's say, 2 random variables, 3 random variables. In this case, d plus 1 random variables. But and then describe how one can estimate the parameters of the distribution. It's actually related to so naive-Bayes model is actually a very is an example of a directed probabilistic graphical model. Okay, if you look at the notes or slides, you'll see that the model is essentially this, right? So there's a y here and a bunch of directed arcs. X1 to xd. Okay. So there was a 2 or 3 node example. 3 node example that we went through in the class. There was this genre of the, I guess, music or movie, and then there were 2 ratings. Right? It's very similar to that. And so all the idea that we had about counting and normalizing is the same idea here. Okay. So estimating the parameters. Here the parameters will be just the probability of a word given class. Okay. So there will be one number per conditional value. So condition on y is confidential. There will be one number for whether the word exists or not, basically, because it's a Bernoulli. And similarly for y non-confidential, there will be one number. Okay. Those are the two parameters. Yeah, and the last part is just trying to say whether independence assumption is a good assumption or not. You can justify that sometimes it makes sense, sometimes it doesn't make sense. Okay. Any questions about the first three parts? Okay. So let's get to the fourth question. So consider this DPGM which has three random variables, and these are the entries. So this is actually, just to kind of, this is the type of thing that you would see in a Excel sheet. Somebody gives you an Excel sheet and asks you to do some data analysis. Yeah, you will not see true false only, but you will see a bunch of categorical variables, and sometimes things are missing, right? This is the metadata information that maybe A leads to B, B leads to C. This is directionality, some additional data. Given that, maybe you can form a distribution, joint distribution. You can estimate the parameters of the joint distribution. Okay, if the joint distribution has exactly this directed probabilistic graphical model, then you can estimate the parameters using just maximum likelihood, right? Because there is no because we know how to estimate parameters in the directed probabilistic graphical model. It was just estimating the numbers in each conditional probability table, as in for each conditional probability, like probability of C given B, probability of B given A, and probability of A. So there are two conditional probabilities and just probability of A. You just need to fill in the numbers. So if you're computing probability of A, you just look at this column, ignore this guy because I don't know the number, and there are 3 false and 3 truths, and the probability of A is equal to 1 is, probability of A is equal to true is 1/2, probability of A is equal to false is 1/2, right? So you just count and normalize. That's what I kind of allude to in the lecture. Okay. So that's the way you do it. Initial parameters of the network, because it's a nice enough network. You just estimate using counting and normalizing. That part should be easy. Anybody facing difficulty for part 1? Okay. So part 2. So I don't recollect. So did we do a problem like this in the slides? One whole column was missing. Okay, so one whole column missing is like a Gaussian mixture model setting. Remember the Gaussian mixture model, you're not observing one random variable at all, which is the latent random variable, which is choosing the component. You're only observing the second random variable x, whatever in values it takes. Okay. So if you remember how to do EM in Gaussian mixture model, it's been taught twice. In 575, for those who have taken 575, we looked at Gaussian mixture model estimation using EM. Okay. In 576 also, when I was talking about in the first lecture, motivating that Gaussian mixture model is an example of a DPGM. Yeah, DPGM. Then we saw how to use EM to estimate it. Okay. So that's that setting. So in this setting, what do we need to do? Essentially, we are if you roughly think of it this way. So if you did not know graphical models business, we are roughly imputing the values that can go here, Z1, and the values that can go at here, Z2. Okay. So Z1 and Z2 can only take 2 values each, right? Z1 could have been true, Z1 could have been false, because we assume A, B, and C are just binary, and Z2 could have been true or false. Okay, so there are potentially 4 settings. You can think of 4 types of data sets, where in one data set Z1 and Z2 are true, in the other data set Z1 is true or Z2 is false, and so on. There are 4 different data sets, right?
Excuse me.
Yeah.
Since for Z2, even whether it's true or false is already inside of the table, because we can see TTF in the top.
Oh, TTF?
And
This
we also
may not be the same observation. So, you're saying that, okay, you'll just infer that because the TTF already there, it's TFF here.
To do the expecting algorithm, that process, I was just for Z1 I include like true, which is TFT and FT inside, but I just don't have the Z2 0 because these are already inside. So in total I have like seven rows to compute the.
So right now how many was that? 3? There are 7 rows already there.
Yeah, but like because the TTF and TFF is already inside, so without that and then add 2 more things, so TFD and FFD, that means we have 5 plus 2, so that's 7. So
sure, I mean you can do it that way. Sure, I mean if you have well written and clearly explain what you're doing, that's fine. Yeah, but see, Z2 is not clear. So yes, I agree that there is TTF and TFF already here, and there is CNF here. So Z2, it's not clear. I don't know how to reason that Z2 can be either T or F, or it doesn't matter at all. It's not easy to reason that. They could be repetitions of observations, right? So, but in a general case, I mean, it's not difficult. You just have to. So EM, remember what is the high-level context EM? EM just says if something's missing. So if some whole row is missing, whole column is missing, they are latent variables. Okay. Here, 2 entries are missing, 2 particular coordinates are missing, then they are latent variables. That's it. So the only complication in this problem is I'm thinking of these 2 entries as latent variables. Okay, that's it. So whenever I have a latent variable, all I need to do is find the posterior probability of those latent variables taking some value or the other. So now it's not just 3 random variables, it's actually there's a capital Z1 which is a random variable, capital Z2 which is a random variable. And I'm saying if I can find the posterior probability of capital Z1, so let me just write it. So the EM procedure would say, okay, in the E step, find the posterior probability of Z1 equal to, let's say, true, given data and current parameters, let's say theta t minus 1. Let's say I've finished the t minus 1 step of EM. You can start with some arbitrary parameters. You also need to find Q of Z2 is equal to t given data. I mean the data is always fixed, so theta t minus 1. So these probabilities you need to find, and once you find them, let's assume that we know them, then the M step all you need to do is MLE with 9 rows now, not as we pointed out, you have 3 plus 4, 7 rows. So 5 of those rows are the same, and wherever Z was there, you just do T, whatever, F whatever, and what was that whatever? So FT, Z1 FT, right? So I'm going to substitute T for Z1 and F for Z1, and these two will be F and T, right? So there will be a weight for this observation, which will be just this number. Okay, this will be the weight, and this number will be the not this number, but 1 minus that would be the weight. Okay, 1 minus that. So it's some whatever weight, 1 minus that would be the weight of this observation. The first 5 rows are the same. All their weights will be 1s. Okay. Now you have a filled, now you don't have any missing data, you just have weighted data set, just to maximum likelihood estimation. So instead of counting, you just have to count, add the weights. So if you have weights here, for probability of A, it doesn't matter because they kind of sum to, they kind of doesn't influence anything. But anyway, so all I'm saying is if you have filled data, then you know how to count a normalize. Okay, now you have a 9-row data set from which you need to just compute MLE parameters. So probability of A, probability of B given A, probability of C given B. Okay. Those numbers you know how to count because you did it in the first part.
Just for the sake of completion,
Yeah.
assuming
No, these are conditional probabilities. These are numbers between 0 to 1. This is a conditional probability. This is the weight. This is the weight itself.
Right? So 0.5.
Oh, 0.5. Yeah, 0.5, 0.5. Yeah, I agree.
So the count would be, since in 5 rows the same earlier
Yeah, so the first 5 rows will be ones.
Yeah.
Let's say ones.
Yeah. Plus 0.5.
And there will be 2 more rows like this for the other observations. This kind. This way.
So there were 3 observations where A is true and 3 where A is false.
Yeah.
So the count would be 3.5 for so A is true.
Yeah.
And the next step.
Yeah. So it's 3 ones were probably already there. There's one more one which came up. Then it's 3 plus 0.5.
And you said that this technique is good for handling missing data.
It's one way. It's one way. Yeah.
Is there a specific kind of missing message addresses? Can you use it?
No, for us in the EM point of view or graphical model point of view, the missing random variables have the same distribution as any other row. So all the rows have the same joint distribution. Okay. So they're not really missing. For us, they are latent variables. We just didn't observe them. If I don't observe them, but I roughly know what the joint distribution is, I can always compute the conditional probability. So theta is the parameter of the whole joint distribution. If I know the parameter, I can compute any conditional probability. In particular, I can find the conditional probability of any random variable. The one that I did not observe, I can always find the conditional probability of that random variable taking some value or some other value. That's what the E step does. Okay, it finds the conditional probability of the latent random variables given the current parameterization of my joint distribution, which is theta minus 1. And the M step, you kind of get a theta t, or theta t minus 1, you get a theta t. That will be new parameterization of your joint distribution. That will just be the MLE solution. Okay. Any questions? I have a lot to cover today. So assignment 3, any questions? This is probably a harder assignment. Any questions about assignment 3? You will get back grades soon. So I think the D-separation property is quite mechanical. You just look at every path and in the set C, they'll pick every node and see whether that is a head-to-tail, tail-to-tail, or head-to-head relationship. Based on that, whether you will kind of characterize for every path whether it's blocked or not, whether it's blocking or not, for that random variable. And if everything is blocked, then it's fine. Then you can say things are conditionally independent. Otherwise, you cannot say. Okay. Yeah.
And they will all in between them.
Yeah.
So do you mean that any of the situation satisfied, then we can say this block, or both should be?
No, either one of them. So you had A and B. So pick one node in A, one node in B, and now you have V's to choose from. So V's either can be in the set C. So let's say you have where is this? Let me just draw it. Let's say there's a and a B. I mean set A and set B, but let's pick a let's say x1 and x10. Okay, there's some path between them. Okay, I mean there may be multiple paths between them, so but per path we'll check something. Let's say this path between them. Maybe it goes through C, or maybe it doesn't go through C. Okay, maybe C is like this, or in the different setting, C passes through. Okay, there's a path which passes through C. Maybe there's a path which doesn't pass through C. Okay. Now we just care about, this is a simpler setting where we care about any node V in C. Okay. So now we have 3 sets of nodes: x1, x10, and V. Now we just ask, okay, V is on the path, V is in C, and V is on the path. Is V connected in a head-to-tail, tail-to-tail, or head-to-head connection? On this path. Forget about the rest of the graph. On this path, if V is tail-to-tail or head-to-tail, then condition on V, this path is blocked. I mean, so if V is head-to-tail or tail-to-tail, this path is blocked. That's it. That's the inference that you did, and then you forget whatever you did. You just remember that there was a path which is blocked. Maybe there are multiple paths between this node and this node. If this is the only path and it was blocked, then you're done. This and this are conditionally independent given C. Okay. The second condition was a little bit more messy. It was saying, let's say there's a path, okay, and maybe there's a node on the path which is a child of some node in C, and then you're just checking for head-to-head connection there. Okay. So B is a child of some node in C, and B is in a head-to-head connection. Then again it's flawed. So it's a mechanical procedure, but you just check whether so if you want to know whether two sets of nodes are conditionally independent, given another set of nodes, just focus on every pair of nodes in the first two sets. Okay, maybe there's x1, x2, but we'll get to x2 later. Let's say you pick two nodes, two specific random variables. Look at all paths between them. There may be many paths, but then maybe there's only one path, and then just check whether the path is blocked or not. That's it.
That is what we do for every combination.
Yeah, I mean, so it's not. So this is something you just code it up, and algorithm will do it, but you need to understand a little bit about. Okay, this is actually mechanical. I can see. So it's basically the reason why they encoded this set of rules is because just from looking at the graph, you will get a wrong intuition that things are conditionally independent or not. Okay, you can read off such things for the undirected graphical model case because you know that a node given its neighbors is conditionally independent of everything else in the rest of the graph. Okay, that's a global Markov property, or local Markov property also you kind of know. But this on the directed graphical model. Directed probabilistic graphical model side, it's a little bit more involved. So you should just not go by intuition by just looking at the plot, just looking at the graph. You should kind of just follow this rule of d-separation. Okay. There is this notion of active trails and stuff like that, which I've not discussed in the class. It's not. You can read about it if you want. There are references in the whole course has like references for graphical models. So look at that book if needed. Okay, so let's come back here. Yeah, I mean, I'm not gonna spend much time on these two questions because these are just Bayes rule. Counting the number of parameters just means the number of values that the p function takes. P is just a probability definition, right? Yeah. So here, maybe in this fourth question, so drawing DPGM and UPGM for this question is easy. Okay, there's only x1 and x2 go to z1. And x2 and x3 go to z2. Sorry, x1 and x2 go to z4, and x2, x3 go to z5. Okay, it's an easy plot to draw for directed probabilistic graphical model. Undirected is also easy. Now, what is 4? 4 is asking. I've told you that x1, x2, and x3 are just Bernoulli random variables, right? With parameter p for all of them. I'm just asking whether z5 is a derived random variable. So, but that's fine. But it also has its own distribution, right? It's also whether z5 takes a value 1 has some probability, and whether z5 takes a value 0 is also another probability, some function of p. Okay, that's easy to write. All I'm asking is there a p for which p of z5, x3 is equal to p of z5 times p of x3? That's the definition of independence. Okay, of two random variables. So I'm just asking, is there a value of p for which this holds? So you can just kind of eyeball and see if there is a p for which that is true. And if it is true, then they can be independent for that value of p. Okay.
Question for the
Yeah.
When you go from directed to undirected, you have arrows. So when you remove the arrows, do you have to connect the x1 and x2?
For parents, yeah, I mean, you can do that.
It's something about the family graphical.
So you're asking. So here you drew a DPGM. You're asking whether I'm gonna convert a DPGM to an UPGM.
When
No, you don't have to do that.
When you do that, you remove the arrows.
Yeah,
you
but
can't just undirected edges.
Sure.
So do we have to also have an edge?
So the rule is basically if there are two edges coming into you, so you are what is it? Tail to tail? No, head to head relationship. Then you just have to marry the parents, as in you just need to add an edge between them.
So we have
But here I'm not asking that. Here, I mean, you can do that, but here I'm just saying, knowing this information, can you directly draw a undirected graphical model? So you don't have to worry about what you did here. You can just directly try to.
Either we have it or we don't have it.
Yeah.
Okay.
Yeah.
Question for the. When you go from directed to undirected, you have arrows. So when you remove the arrows, do you have to connect the x1 and x2?
So parents, yeah, I mean, you can do that. Okay, so and 4 is a little bit involved computationally, but again, all the conditional properties have been given here. It's just reading this notation might have been a little bit difficult. This is kind of easy. X2 given G2 or X3 given G3. These are just normally distributed random variables. So X is normally distributed, conditionally normally distributed. This one seems a little bit difficult. It's nothing. It's just saying conditional probability of G2 taking the same value of G1, given a value of G1 is 0.8. So let's say G1 takes value 1, then G2 taking a value 1 is 0.8, and G2 taking some other value is 0.2. So this completely actually tells you what the joint distribution is. Now all I'm asking is compute some conditional distributions. They might have been hard here because it's an assignment question. So hard in the sense you might have to kind of go from this conditional distribution to relate it to the joint distribution. And once you know the joint distribution, you know exactly what numbers you need to fit. Yeah, I think all questions are like that. Both the questions are like that. Okay, so it's a computationally involved question, that's all. And number 5. So number 5 is an implementation question. So any issues with this? I mean, the message dimensions were just I think 2-dimensional. So if you understood the general algorithm or even the specific case in 2 dimensions, with these as the factor functions, okay, then you're fine. You can actually hand compute this because it's only just 2. So if you cared about finding the what was it? Finding marginal distribution. So right, we want to find the marginal distributions of all the random variables. Then you can hand compute it because just 5 random variables, you can always do summation and figure out what the solution is, okay, what the marginal is, and see whether your algorithm is giving the same answer. Same thing with Gibbs sampling stuff that we saw. Okay, so that's fine. So both assignments are fine. Okay, so we'll start today's lecture. Okay, so today the objective is to kind of we can make it a little bit, so we have lost some time. So the objective today is to kind of close the loop in terms of how we have started from deep learning, which is a supervised learning set of tools. In between we looked at RNNs and GANs, which can also be used for unsupervised learning. Then we looked at structured learning, which means graphical models where you have metadata, you're thinking of everything as random variables, and the base object of interest is a joint distribution. And then in the last couple of classes, we said, okay, let's not worry about estimating distributions, let's worry about taking good decisions. Okay, so A/B testing was about a particular form of decision-making problem, right, where you had a choice between 2. So you actually do a randomized control trial, randomly split an incoming user, for example, onto each of the 2 choices, and figure out and do basically a 2-sample hypothesis test to say whether there is no improvement of the second choice compared to first, or maybe there's an improvement. Okay, and then we saw multi-arm bandits. There were several algorithms that we saw: epsilon greedy, multi-arm bandits, epsilon greedy, UCB, upper confidence bound, Thompson sampling. But more than them, the key thing that we were trying to capture in that setting was the notion of rewards only. So we wanted to learn, but learning the parameters of the arms. What were the parameters of the arms in the stochastic setting? The parameters were the mean rewards of each of the option. So each choice, each decision gave you a reward. That reward, in one of the settings was stochastic, in the sense, if I pick the first arm, maybe the first arm's reward is a number from a distribution. Maybe it's from a Gaussian, maybe it's from a Bernoulli. Okay, it's a number. And since in every realization there can be different numbers, I'm just focused on, okay, each arm or each decision will have a mean value of the distribution. I only care about the mean value. So that's the number associated with the decision, but I don't know those numbers a priori. If I knew the numbers a priori, mean rewards, then that arm which has the highest mean reward is the decision I'm always going to take. Okay, but I don't know these numbers. If you were thinking from a learning perspective, as in just estimation perspective, then you would say, okay, I'll try the first arm 10 times, second arm 10 times, last arm 10 times, and then get an empirical average reward, and then hopefully one of them is higher, so you will say that that's the arm that I'm going to use. But we are not focused on the whole point of multi-arm bandits was to say that, okay, let's not do this, because that means I have to try each arm several number of times, and I don't really want to just care about estimation. Estimation would be just estimating the means of the arms. I actually care about taking decisions. Okay, maybe I have 10 rounds to take the decisions. I have 10 decisions to take, 10 sequentially, same setting again and again. I just want to compare the decisions that I take to the best decision in hindsight. Okay, the best decision in hindsight is the one arm which had the highest mean reward. But now I'm going to take a sequence of decisions. Okay, not to learn the mean rewards, but take a sequence of decisions such that the gap between the decisions that I took and the best decision I could have taken always is low. Okay, it's a different objective. The objective is focused on how far are your decisions compared to the best decision in hindsight. Okay, that was the notion of regret. Or you can just think of me taking just decisions, the total reward that I get, expected reward, that should be as high as possible. Okay, so rather than estimation, the focus was on take the best decisions as much as possible, ideally. Okay, so to do so, we had to not just learn or estimate the parameters, estimate the mean rewards. We had to do what I didn't harp on it too much. I mean, I didn't spend too much time on it. It was called exploration and exploitation, in the sense that exploration just means that in epsilon greedy, for example, exploration would be that scientist version of the problem, where with some probability you just pick a random arm, because that will give you an information about what's the reward of that arm that you picked. Okay, that would be exploration. Exploitation would be the businessman version of it, where whatever information I have, let's say the average reward for the first arm is 3 units, average reward for the second arm is 4 units, and so on. Then you just pick the one with the highest value. Okay, that's exploitation. So you had to do this exploitation to take best decisions as close as possible to the best in hindsight. Okay, that was the trick. Not just learn for all the T rounds. So after all the T rounds, you would have taken arbitrary decisions, but you would have learned something. But that's not useful, because I care about taking a sequence of decisions which is as close to the best as possible. Okay, cumulatively. Okay, so that was the distinction. Bandits are used. The big consumer of bandit setting is online advertising, for example, clinical trials, and so it's a multi-billion-dollar industry. So it's good to know this. And then we said, but bandits, you think of repeating the situation again and again, and there is no notion of context. So I was giving the example of MSN.com, and I said, okay, maybe there's a user profile which also comes when the user visits the page. So then we said, okay, if there are contexts involved, then I have to go from context to a decision. Okay, I can't just take a decision arbitrarily in every interaction. I have to go from I have to use the context information. Context is just a synonym for state. Okay, and so when I say this, I have to learn a way to go from a context to a decision. I'm actually asking for a function, because it basically means for different contexts I have potentially different actions. That means I need to completely specify a function, whose input is the context, output is the decision action. Okay, so we looked at one algorithm called exp4 for that. It was basically just maintaining a bunch of weights on these functions or policies, and it was somehow trying out actions based on these weights. There was some summation involved. It was creating a distribution of actions. It was trying out an action, and based on the feedback for that action, it would update the weights of these policies. Okay, so you just go back to those two slides, a few slides, and look at it. It's not a very different algorithm. So that was the contextual bandit setting. And then we said the last lecture, the whole process was contextual bandit setting. You take a decision, has no consequence on the next context that you see. Okay, but in real life, actually, there's a consequence of decisions that you take, which are long term. For example, you're a retailer. You set prices to be too high, and people see that, they respond. Of course, they respond in the current period, but they also respond by not coming to your store in the next subsequent periods. Okay, you chase away the demand. So there's a long-term consequence of the decisions that you're taking now. Okay, so to model that, we looked at the object called Markov decision process, right? And we said to learn in the setting. To make good decisions in the setting, similar to in the bandit case. Bandit case, to make good decisions, we were trying out, right? With epsilon probability, we would try random arm in the epsilon greedy setting, or we would, with 1 minus epsilon probability, we would try the best arm. So in this long-term consequence situation as well, which we used an MDP type of a mathematical notation represented, but essentially the problem is called reinforcement learning, where you would again try different actions in different contexts or states, okay, and somehow learn the best mapping from a context to an action, or a context to a decision. Okay, so we kind of sidelined the. So the objective was to maximize the total reward collected, expected reward collected. Again, similar to bandit setting, and but we dropped the notion of regret. So we wanted to maximize the total reward collected, and we saw one algorithm called Q learning, which would maintain what are called Q values. I'm going to repeat it in the next few slides, but just to give a high level idea, there was an algorithm called Q learning, which would maintain something called Q values, which are values for every state and action, or every context and decision. And somehow that algorithm was able to kind of maximize the total reward collected. Okay, it would be able to find a policy, as in a mapping from a context to a decision. That policy would be good in the sense of it would maximize the expected reward collected. Okay, so that's where we kind of introduced this notion of Markov decision process and Q values. So if you go back to Markov decision process and think only of supervised learning, so okay, I don't want to think of decisions, I want to just do learning. Then you would want to just estimate these, for any given state and action, can you predict the reward? For any given state and action, can you predict what next context would be? Those would be prediction problems. Okay. Given the context, given the action, tell me what the next context can be. Given the state, given the context, given the action, tell me what the reward could be. Okay. In the MDP, there were states, actions, transition probabilities, which were this, rewards, and there was a gamma, so don't worry about the gamma. So MDP was this. The learning problem would be just focused on trying to learn the transition probability. Given a state, given action, tell me what the next state can be. Or given a state and action, tell me what the reward could be. So these are the quantities you would just learn. Okay, then this can be cast as supervised learning. Okay, but but we are not focused on learning. We want to maximize over some policy pi of the expected total reward that we get. Okay, RT. Okay, t is equal to 1 to infinity maybe, and then there will be a discount, something like that. Okay. So this is our objective, and Q learning lets you find a pi, find a policy, which will kind of maximize this objective. Okay. And why? And that's a little bit roundabout way argument. What we did not show, and it's in theory, is that Q learning maintains some Q values. These Q values at time t, if you make this tends to something called Q star. Tends to what are called optimal state action value functions. Sorry, optimal state action values. Okay. So Q learning is doing some iterative updates by trying out different actions in different states. These numbers, for every, think of this as a matrix. Okay, for every state, for every action, there's a number. This matrix is going to another fixed matrix, which we don't know. This matrix essentially corresponds to some pi star. Okay? In a sense, so let's say this is argmax of this is equal to pi star. Then pi star is nothing but argmax over A. Sorry, let's say pi star of S is argmax over A of Q star of A comma S. So if I knew this matrix, then I know what the best policy is. And this best policy, there are two ways to write it. The best policy would have been the policy which would maximize my total expected reward. But instead of directly solving this optimization problem, it's an optimization problem. You can, I'm searching for policies of some objective. Instead of doing that, we are saying, okay, we'll maintain some Q, we'll define what are called state action value functions, which just says how valuable is it for me to be in some state, take some action, and follow some policy. In this case, it's going to be the optimal policy. Okay, that's Q star. If you can somehow compute Q star, then the best policy, which is the mapping from context to decisions, and Q star is related this way. Okay, we saw this equation last time. So that's the story so far. The first two, till up to the previous lecture. And today we're gonna do something light. Hopefully, there's only one interesting, couple of interesting techniques. But what we're gonna do is essentially, okay, there's some state action value function. We're gonna try to approximate that using function approximation. They just call it function approximation. So any matrix, you can approximate it by function, a parametric function. Okay? I'll kind of describe what it means to approximate this matrix by a parametric function, but let's say we can do that. Then once we can approximate something by functions, we can pick linear functions, we can pick nonlinear functions, and we're going to pick specifically neural networks. Okay, so that's going to be the relation back to neural networks. That's the function approximation that we're doing here. We're going to pick neural networks, and then we'll see that the game playing agents that we saw videos last time, especially for Atari games, the breakout is the only one we saw. There's also, I think, Doom also we saw the video. We'll focus on what's the situation, what's the Q. So it's going to be we're going to use neural networks, but we will still use the Q learning update rule that we saw in towards the end of last lecture, and they call it deep Q network. Okay, DQN agent is a deep Q network agent. The Q function is approximated by a neural network. So we'll see how they do it. We'll do that, and then we'll get to more recent advancements in reinforcement learning, or more recent advancements of how to do decisions in really complicated state spaces. Okay, if there are too many contexts, okay, like in a board game, in this particular case Go, the board game has too many contexts, too many board situations. Okay, given any situation, what's the best move you can make, best action you can take? Okay, why board games? Why not real life? Because in board games things are more structured. It's just driven by the rules of the game. So they've been able to make a big leap here, and hopefully that will kind of influence other complex decision-making settings where you can create autonomous agents, essentially things which are really AI agents which can take decisions. Okay. So is that part clear? Whatever I said. Okay. So with that 1 hour intro, let's take a break for yeah, 7 to 8 minutes, and then resume. Okay. Okay, so let's actually start. So value function approximation. So let me directly get to the Q learning algorithm. So remember, it was so towards the end of last lecture I was saying there is an algorithm which will let you maximize the cumulative number of rewards. So you can think of, so Q learning algorithm's base object is this Q function. Q function is in terms of intuition, Q function is just the expected reward that you can collect starting from a state and a given action and applying some policy. Okay, so that's what a queue function is. So if you want me to write the definition, so Q for a given policy pi of s comma a is just the expectation of reward that you get from applying an action. Action A and in the state S, plus all the rewards that you would collect from next time onwards. Some applying policy pi. Okay, I've messed up the notation, but what I'm saying is Q pi of SA is just saying how much do I value this state and a given action. All it's saying is in this state, and if I take this action, I'll get some immediate reward. And then my value for the state and action would be my immediate reward plus all the rewards that I can get, which is basically sum. Maybe it's sum to infinity or something like that. All the rewards I can get by following some policy pi. Okay. Because you need to say what policy, how are you going from one context towards the action, how are you going to the next context, and so on. So that's why there's an expectation. The notation is a little bit messed up, so don't try to follow that notation. So that's the Q value. So that's why it's called, this is a Q value. It's just a state action value function. Just like there was a value function, which was just how valuable I find a particular state to be, V of S. Instead of that, there's a Q of S comma A. And so Q learning algorithm is just trying to, it's called learning because it's trying to learn little Q star, remember? There was a little Q star, which was satisfying the Bellman optimality equation. It doesn't matter. So we want to find, Q star, or let's say Q little star. The Q learning algorithm is just trying to learn this. If you learn this, then we know that the greedy policy, which means that if I know these numbers in my table, then my decision to make at every given state is just the maximum of all the that number. So there will be, let's say there are 3 actions, there will be 3 numbers in that given state. You take the action corresponding to the highest number. Okay. So that's the greedy policy. If you knew this, we don't know this. That's why the Q learning algorithm is learning this. Okay. And how is it learning? For every situation, it's going to do something like epsilon greedy. With some probability epsilon, it's going to do random action that is permissible in that state or context. And with some other probability, it's just going to be greedy. It's just going to take the action that has the highest value in the current table. So maybe the table is each row is a state, each column is an action. Then you look at that row corresponding to ST. There will be, let's say, 3 numbers. Pick that action corresponding to the highest number. So epsilon greedy. With epsilon probability, you're just randomly picking an action. With some probability, you are picking the greedy action. It's like epsilon greedy, but in the second. And there's an interesting update here, which is like a moving average. So if you kind of rearrange terms, so if you just think of this is basically 1 minus alpha times the previous Q value in the current index, current location. Okay. Think of this Q table with maybe ST is this one, maybe some AT is this one. So this is the number that you're updating. Okay. So you update this number by saying the new number is going to be 1 minus alpha times the previous number plus this new thing, which is going to be a function of which next state did you land and how much reward did you get currently. Okay. So this has an update, and we didn't really go into why this is the right update and whether it makes sense and all that. We just intuited about it from value iteration. Value iteration was a algorithm for the MDP setting when you knew the transition probability and the rewards. Okay. Anyway, so there's an update equation. You update the numbers. These numbers converge to Q star. Okay. And if you know Q star, you know exactly what's the best policy to act in every situation or every context. Okay. Now, Q learning is not enough because it's illustrated by this example where we are saying, okay, if you have a environment like this, okay, it's a 2D world, so you can think of state being one of the cells, okay, like you are here, maybe this green part here. So you can denote it as x1, x2, some coordinate or some cell identity. Okay. But in reality, things are like this. The robot may be looking at an image, or it has a video. It's looking at some very rich information. Okay, then it's kind of hard to tabulate. Think of a Q table. What is the state? The state is going to be what the robot is viewing, and what the robot is viewing is a 1000 cross 1000 pixel image. Okay, you cannot say for every 1000 cross 1000 pixel image I'm going to have a number. That's going to be like too huge. So and that leads to the idea that we can approximate. So we cannot have a really large table. Okay, so remember Q was a function of st comma at, or in general for every state and action there has to be a number. So previously I just motivated it as a table at for every s and for every a there's a number. I'm just saying that now let's just think of this as a function itself. This is a function of two arguments, state and action, right? So if we're going to think of this as a function, we're going to see that we can approximate it by any type of function. In particular, we're going to approximate it using a deep network. Yeah, this Q function is actually just a value function. Policy was also a function going from states to actions. So you can think of that as a function. Then that can also be approximated, and the model itself can be approximated. Let's not worry about these 2 points. So why am I saying approximated? Because if you think about it, the problem is maximize cumulative sum of rewards, and for every state for every action there is actually a Q star. So that Q star can be computed using Bellman's optimality equation. I have not written it here. So that would be the right function. Q star would be the right function that you want to get to. Okay. But when I so there's little Q star, or in the previous slide I think I used Q star. So it's the same thing. So there's a right function that we care about. If you knew this function, then we know how to take an action. Okay. I use the word approximation because now when I say I'm going to only look at these 2 argument functions, which are going to be just linear functions, some quadratic functions, or maybe even approximated by maybe using a neural network or something, then those are some specific functions. Okay, they may not be able to completely represent these guys, as in these are the functions that come out of that satisfy the Bellman optimality equation. Remember there was the Bellman optimality equation last time, some equation, okay, nonlinear equation. If I arbitrarily say, okay, I'm gonna instead of thinking of this function, I'm gonna think of a linear function, that may not satisfy the Bellman optimality equation. So that's why I'm saying it's an approximation. Okay, so it's not very okay. So in pictorially, all I'm saying is you have this box. You had Q of s comma a. So for every state in action, you were supposed to tell me what that number is. Q of s comma a. That's a function. I'm going to make it parametric. In a sense, it's going to be Q of s comma a with a parameter w. So it's going to be a parametric function. So given the 2 arguments s and a, it will tell me what the number is. Okay, and I use the parameter w to kind of allude to the fact that this is going to be a neural network. Okay, so you can have arbitrary functions, things we have seen. This is the one that we care about today, and these are all the functions that you can think of. Okay. So what are these functions? Their input is going to be a state, for example, an image, and an action. For example, action is something discrete like 1, 2, 3, 4. Let's say, given the image and 1, 2, 3, 4. You have to tell me what that Q of s comma a would be. Maybe it's 3 units or something. Or there's a slightly different version which also does the same thing. It's basically given input image, like what the robot is seeing. Tell me what's the value of taking action 1, what is the value of taking action m, and so on. Okay. If there are m actions, for each given the image and the action that I can take, what is the value of doing so? Okay. So this, as you can see, it's like an image as an input and a bunch of numbers as an output. So you can think of this as like a neural net, a classifier. In fact, you can use a CNN, for example. This takes input as an image and outputs a bunch of numbers. That's what a CNN is actually doing. CNN is just going from an input image to a bunch of numbers. Those numbers happen to be probability, PMF. Because of this softmax operation, these numbers happen to sum to 1, but we don't care about it. Okay.
So if we are using linear decision tree, we don't have weights.
No, linear will have weights, right? Linear. So it's linear just means my Q of S comma A times. So I have an example, I think, in the slide. Linear just means this is equal to W transpose some vector like S comma A. Something like this. Huh? I said linear just means something like W transpose S comma A as a vector. I mean, linear just means it's linear in the parameters. A neural network is not linear in the parameters. There's a lot of non-linearities, right? That we saw. Okay. Let's see, is this important? So let's come back to this later. This is just showing some gradient rule update for how to update the weights, but I'll put it in the context of DQN, the actual agent that we want to look at. So yeah. Okay, I mean, so before I get to DQN, let's understand this slide. So previous slides are just saying if you had a function approximator, how do you figure out the weights of that approximator? But that's not very difficult. So let's come back to this Q-learning update rule. This was the update rule, right? You are at a situation A. You are in state ST. You took an action AT. You landed in next state ST plus 1, and the simulator or the environment told you what the reward is currently. Maybe it's 0, maybe it's not. So given this, you would update the Q value like this, right? And I also told you that if you do Q learning, eventually the Q values will be Q star, some one number. Right? For every pair, there will be one number, fixed number. Okay. That means that if you have reached that fixed number, then there should not be any update. Right? This is a fixed number. This should also be a fixed number. This should also be a fixed number. Right? And so this update should have same numbers over here. Right? Or in other words, if this number is equal to this number, then this should be equal to 0. Okay. In a sense, if Q learning has figured out best Q stars, then there has to be no update. Essentially, this term should be equal to 0. Okay. Or that you can say, I mean, I put an expectation because I've used capital letters here, and capital letters means these are random variables. Okay. You took an action AT at ST, you would probably randomly draw land somewhere, right, at next state ST plus 1, and you may get a random reward RT plus 1. Remember? So that's why I put an expectation. At optimality, essentially, this error term, or this is called temporal difference error, some error term, is equal to 0. Okay. So this gives us an idea of how to update the weights. Okay, now I'm going to say, okay, this is a Q function here, there's a Q function here. It's the same function, so I'm going to put a comma W in both sides. Okay, because I want to approximate them by some parametric function, could be neural network. And then I'm going to say this, because at optimality this has to hold, then I'm just going to update my W. So what do you mean by that? I'm at state ST, I took an action AT, I went here, and I got this reward. I'm going to update my W such that this number is small as possible. Okay. So basically update my W such that this side minus this side is very close to each other. Okay. So that's why I put a W. And you'll see that in DQN, what they do is they only update W's, not both sides, they update on one side. So I'm going to explain that in the next few slides. Okay. So all I've said is at optimality you need this to be 0, right? And if this needs to be 0, then you can imagine some sort of if this is the error, this needs to be 0. You can think of setting the parameter such that this term, this sum, this negative, this difference between two things is close to 0. So again, it's like a least squares objective. I'm trying to say, if I want this to be 0, I can explicitly say I want to set W such that this is equal to 0. Right? That's the motivation for updating W. Okay. Because we can't update Qs anymore, like directly. You can't apply this equation because the number of states is too many, all the images. We can't, for every image we can't maintain a Q value. So we have to only now play with W's. So I'm gonna explain a little bit about basically the next couple of sets of slides are about case studies essentially. So DQN is a specific example of which started in 2012, I think, or 2013, and ultimately there was a Nature paper in 2015. And so they created, these guys at DeepMind, they created a agent which could play about 50 games in the Atari games environment. And I'm gonna illustrate how they do it. So they kind of mix. So I just told you that you can approximate the Q function, and I told you the Q function. So I told you the Q learning algorithm. So those two, it's not clear how to directly use those two. Okay, and I mean maybe there's some idea, but I'm gonna tell you that it's not clear how to mix them, and I'm gonna tell you in DQN how do they mix these two parts, doing a function approximation and doing this Q learning update. Okay. Okay, so what is the issue with direct function approximation? What's the best way to say this? Okay, so just minimizing this mean square error, I was telling you there was an error metric that I said I can update W such that minimize that error. Directly minimizing that is messy because data is not IID. So you can't really think in terms of intuition of a supervised learning problem, like minimizing mean square error. Okay, so they do some couple of tricks to kind of deal with this data issue, as well as I mean, this is just a fact for reinforcement learning, that your current action is going to influence your future trajectory of the data. Okay, so there is dependence of the data, for which you have to carefully think of how you're going to do these updates of the W parameters. Okay, so let's directly actually see what the DQN agent is. So first things first, so I'm gonna kind of skip YDeep representations because you'll see that for the Atari game, our input is gonna be just a screenshot of this game. Okay, there are actually 50 different games. I think breakout is somewhere. I don't know. Oh, this is the breakout, the diagram that you're seeing. So the input to the agent is gonna be just a screenshot, as in it's gonna see the video game as if human is seeing. Okay, so that's the input. And the output of the algorithm is going to be what decision to take. In this case, the joystick decision, left, right, up, down, and fire and so on, right? Okay, this is just what I just said, and so DQN will use Q learning that we saw last time, and is going to use function approximation. And in particular, it's going to use a CNN as a function approximation because the input is the screenshot. Okay, it's a screenshot. It's a stack of screens actually. In reality, it's 4 screens. Okay, they're sampling the screens at some rate, and there's four screens, the current screen and the previous 3 screens, let's say. And how is it going to mix function approximation with the Q learning update? It's going to be that it's going to do something called batch optimization to update the weights. So first of all, Q learning, so the Q function was already approximated with weights through the CNN, right? CNN has weights. Now we're going to update these weights using something called batch optimization, and you'll see what batch optimization is. And it's very similar to what we do in supervised learning. And there's also a second trick that they use, which is called freezing of targets. Okay, so I'm going to explain what, batch optimization is quite straightforward. I'll also tell you what freezing of targets is. And these two extensions are just so that with the function approximation, the Q learning is not arbitrarily coming to arbitrary Q values. It's pretty stable, and it'll get to good Q values. Okay. Okay. So this is just an example of, I guess, specifically in that architecture, what was the input. So the input is going to be a stack of raw pixels from the last 4 frames, which I just said. So there are 4 images. Okay, 84 cross 84 is the size of the image, and there are 4 such images. And this is exactly the specs of all the, it's not a really deep network. It's just 2 convolution layers, okay, with ReLUs, and 2 fully connected layers. Okay. And output in this case is given this input ST. Output is going to be there are 18 joystick actions that you can take. So it's going to be 18 different numbers. Okay. And if you are greedy, whichever number is the highest, you would take that action. If the network is already trained, let's say the weights are already set, then given the recent 4 stack of frames, just take that action which has the highest number. Okay, if the whole thing is already trained. Okay. So now I'm going to tell you those 2 tricks. What was that? Batch optimization and freezing of targets. Okay. So batch optimization has something to do with what is called experience replay. So I'll just explain these phrases. Batch optimization, experience replay, same thing. And then freezing of targets and fixing Q targets, the same thing. Okay. So in Q learning, we'll just do as usual. We'll take an action 80 according to whatever the Q value that we have. It's a function approximated Q value, but still we can take action 80 according to the according that action which maximizes the current Q value at the current state, or we can take action at random. Okay, that's what is the epsilon greedy policy. Right? You can either take an action at random in the current state, or you can take an action according to the highest Q values that you have. Then what you do is you actually store. You don't do the Q update immediately. Okay, that's now we are bringing in the use of Q function approximation. That's why it's different from the previous Q, just vanilla Q learning setting. We're going to just store a 4 tuple, which is what was the state, what was the action that I took, what's the next state, what's the reward. Okay, I'm just going to store this 4 tuple in a database essentially, and they call it replay memory. Okay, I'm just going to store those 4 numbers, and then what I'm going to do is I'm going to sample a bunch of such 4 tuples from this memory. Okay, from this database. So let's say I've already done a lot of different things. I've stored these such 4 tuples, many such 4 tuples in my database. Okay, I'm going to sample a few of them. And why would I do that? Given a sample, I'm just going to do some weight update. So remember, we have to do, only way we can improve the Q values is by doing weight update, right? So we're going to do weight update. So how are we going to do that? How do we update the weights? We're going to do some sort of a least squares objective. We're going to define some sort of a least squares objective. On the objective, we'll have something called targets. Remember in supervised learning, the y's were the targets. Y's are called targets, and f of x is called your prediction function. So for us, we'll have some targets. Okay, these targets we're going to define using some old fixed parameters w superscript bar. What do I mean by that? These numbers are what I'm calling targets. Okay, and this number is my prediction function. Okay. So what I'm trying to do is optimize or minimize the mean squared error between targets and the Q network or the Q function. So Q function is parametric, right? It has W as a parameter. Let's say we are in the ith iteration. Okay. We are in the ith iteration of updating these weights. Okay. So what am I going to do? I'm trying to search for the best weights of the Q network. This part is kind of clear. I'm trying to find the best weights. But how do I define what best is? I'm going to define what best is by defining some fixed numbers. These are going to be fixed numbers because I got a mini batch of such 4 tuples from my experience replay database or replay memory. Okay. Because I got these 4 numbers, I can compute these guys. Because I said these parameters are fixed. They are not optimization variables. So if these numbers are fixed, I know S prime, A prime, R and S. So I know exactly what these numbers are. Okay. So these are going to be my y's essentially. And these are going to be my f theta or fw of x. Okay. S and A is given. I want to find w. So this is how I'm going to update my w. I'm trying to find a new w such that these numbers are going to be close to these numbers only on the batch that I sampled from my memory. I'm just calling it memory. Just think of it as I'm trying out different things, but I'm remembering this 4 tuple of state, action, next state, and reward. Okay, I'm collecting a bunch of them, and just think of it as over those 4 tuples, I'm trying to minimize the difference between my target. I'm just calling it target, but it's just the just think of this as the. Remember in Q learning, this was in fact this in Q learning this whole thing is the error. Okay, except we just said now we're going to make it parametric, so we introduced W's here. And I'm also doing one additional trick, which is fixing the Q targets, which is that I'm saying that let me not make this a variable anymore. If I put W both sides, W is a variable. That's what I want to minimize over, right? So this is a loss function. I want to minimize over W, but I don't want to make this a variable. So I'm going to freeze this to be some fixed number from before. Okay, and that's what fixed Q targets. And experience replay just means this is how I'm going to try different things, store it in a database, and subsample a bunch of numbers from the database and look at this type of an optimization at every update. Okay. So those are the 2 things that they introduced in this paper. One example is not 4 previous actions. One example is that state, action, reward, next state. 4 tuple. 4 previous screenshots, and that's every consecutive set of screenshots, 4 screenshots is called S there. So here state is not just the immediate screenshot. For some reason, you can look into the paper, it's 4 successive screenshots, not the immediate screenshot. The immediate screenshot, previous one, previous one, previous one. Okay. There's some rate at which they are looking at the screenshots. They just chose it to be 4. Okay. Yeah, there's a lot of design choices, right? Why 4? Why not just current screenshot? There are a lot of things that anybody can do, but for this setting, they've gotten really good accuracy, and I'm going to show the plot very soon. Okay.
What is S prime?
S prime is the next state. Remember, you're in state ST. You take an action AT, get a reward, go to the next state. You just remember this 4 because these 4 are related to each other, right? You went some state, you took an action, you went to the next state, and you got a reward. That's like the basic unit here. So experience replay is just saying, okay, you did this, but what I'm going to do is I'm going to put it in the memory. But when I put it in the memory, but I need to update Q value. Okay. So in the vanilla Q learning algorithm, you would get this, and you just directly update Q of S, st, right? Here you are not doing that. You're putting this 4 tuple into memory, subsampling a bunch of such 4 tuples. Okay, getting a batch of such 4 tuples from memory. Maybe the memory is huge. It has maybe 100,000 entries. I don't know. Capacity for 100,000 entries or something. Such thing. You'll subsample, let's say 100 of them. Then over this expectation is just saying, on all those 4, all those 100 such examples, I'm going to minimize a squared loss. That's all it's saying. and the square loss is going to be basically the temporal difference error, the Q-learning error, but I'm going to not make this W also variable. Because this is also Q, this function, this is a Q function, this is a Q function. I don't want to make both sides a variable. They chose to make this, they chose to set these weights to be some fixed numbers, these weights to be fixed numbers, which were from, let's say, frozen for a few episodes. Concrete example is, let's say 100th episode you got some weights, you keep them fixed. For the next 10 episodes you keep updating this, but this is always fixed. And then after 10 episodes you update this to the newest weights and keep them fixed, and so on. So they just want to make these targets not moving too much. These are called targets because you can always compute this. Just think of this, once you compute this, these are y's. You can ignore the whole formula here. Okay? These are y's, and you're just asking, finding a W such that this, for this input, this function predicts the target. It's one number.
The size of the number
It's also arbitrary. I don't remember what they do. There's Nature paper in Nature 2015. We can look at it. I have reference at the end, actually. So this is just a pictorial diagram of what's happening. So actually, let me just spend some time here because this actually it's a block diagram. So there's a Q network. Okay, that's the Q function. If we learn the Q function, then we don't need anything else. We're just going to directly interact with the environment. We just take the Rmax of this Q function, take the action, see the next state. Take the Rmax, see the next state. Take the Rmax. I mean, once you've already learned everything. If you knew the best Q function, we just take the Rmax, see the next state. Take the Rmax, see the next. But here we are learning. We're trying to learn how to what's the best thing to do in every situation. So we'll take that. Let's say currently there's some Q values. We'll take an argmax according to it, or take a random action. So here I'm just showing the greedy policy, but it's actually the epsilon greedy policy. Take an action, okay, to the environment. Environment will tell you what's the new state. It also tells you what the new reward is. So you are in the state, you took an action. It tells you what the reward is. It tells you what the next state is. Okay. Next state you can kind of is put back here as well as here. I mean, actually here. I don't know what is it. Okay, so you have this 4 tuple. Okay, you just remember those 4 tuples. Okay, you keep remembering such 4 tuples. Remember, it's a database, one row in a database. And then what you do is, so that's you had a current weights of this Q function. I want to now update it. Okay, the way I'm going to do it is I'm going to look at this tuple, some subsample of some let's say 10 or 100 of these. I'm going to now pick only 100 of these, okay, from the memory. I'll take 2 of the arguments, S prime and R, okay, to compute the target, the Y. Okay, the Y has some weird form, but ultimately is some one fixed number. Okay, and compare Q's prediction on Y for the S comma A in my memory. Okay, the 100 samples had S comma A as well, right? So I'm feeding S comma A and saying how well it's predicting the Y. And I'm trying to update the weight such that the prediction is close. Okay, that's written by this last one. Okay. So Q of S comma A has a theta. This diagram is from a different presentation, so it's again theta instead of W. So think of these as Y's, okay? These are just fixed Y's. I'm just trying to update theta such that this prediction is close to Y. Okay. Update the theta, that's all. And that you can use gradient descent or something to do that. Okay. So this plot is not readable much. It's not much readable, but basically this is a sequence of. This is just a set of games. Okay. And this is trying to show. This plot is trying to show how well their agent is playing the game. So each index, x-axis index, is a game, and they have the same agent in the sense that it's the same neural network, same two convolutions, 2 fully connected layers, same hyperparameters. Not same hyperparameters. Retrained on every. So hyperparameters could be this, 4. It's not exactly that, but learning rate and so on. You train, so it's the same network architecture basically, same ReLUs and so on, except the weights are learned on per game, and it's showing how well. So blue is their performance. The y-axis is in terms of percentage improvement over human. Okay. So human is at 100% level. So on the y-axis, this is the scale. At 100% is the human level. Okay, professional human level, and it's showing. Of course, there are some games. So there's blue is this new agent, and gray is a linear function approximated agent. Linear function approximated means not using the neural network. Given the input image, have some sort of a feature engineered linear function which says given the input or 4 images, what would the action to take? Okay, it's a linear function linear function approximator instead of a neural network CNN approximator. So the gray is that one. You can see that mostly gray is not doing that well compared to, in one case it is double down or something. This is the human level, and this is saying we'll consider things good enough if we are within 75% of human level. So anything above 75% is a vertical line, just to kind of say that because they're professional human level, right? So they're showing that from here onwards you can see a lot of games for a lot of games. In fact, you can have 25 times improve, 25 times more score. On average compared to professional human in some of the games. Video pinball, boxing, things like that. So that was remarkable in the sense before this, first of all, even merging any video based sensory measurement to taking actions and really doing well was not documented, I guess, or it was not that successful before. People had made agents which could play Tetris, chess, and all those kinds of things, but not these things. And now you see things with Doom and so on, right? And as I said, games are just a test bed because you have a simulator. If you had a real world simulator for, let's say, an inventory management setting, okay, then you could actually figure out for every action that you took, how the future is going to evolve, and figure out what's the best action you take for every context that you have. And then in real world you could do that. Okay, so ideally would like to have a simulator for doing this, again, learning such complex policies. For every context, what's the decision? Any questions? Or is this too confusing? Okay.
So these approximations and using neural network can be used in real world because
it can be. It can. But in real world, so each game you probably interacted with, let's say in this case, video pinball. It interacted by taking an action, dying eventually, restarting the game, trying different actions, dying eventually, and so on. It probably did it like millions of times. You can't do that in real life. That's the only issue. You can do that in real life for some settings, like ad display or something. Because you have millions of impressions potentially if you're a large property, web property, right? Okay, so this part was just saying there is a Q-learning algorithm which will give you what's the best thing to do in each context, and this part is saying people have shown it to work even in very complicated settings where actually the input is just images or video stream essentially. Okay. Here they're just and people have looked at parallel architectures and so on. So if you wanna work at Google and all that, this is the kind of thing they do. Not so much on the algorithm side. Basically previously, the performance that I showed for each game they had to, maybe for each game they had to train 14 days straight on whatever hardware they had, and they kind of do some parallelization to move it to 6 hours per game. Okay, so that's more software engineering actually. Any questions at this point? About anything fundamentally that you are not understanding? There's of course some details that I glossed over, but DQN was essentially 2 additional tricks of using a function approximator and trying to use some sort of a least square loss, with one side fixed as targets and the other side you want to update the weight. So you just do gradient descent there. Okay. Okay. So next, I'm gonna just introduce AlphaGo. Maybe, because we only have half an hour, I'll probably not go into too much details. So AlphaGo has, by the way, several versions. Now the latest one is called Alpha 0. So this was the version. The version I'm going to talk about today is going to be from 2016, which competed with one of the top players in Go, Lee et al. After that, there was AlphaGo 0, and then after that, which happened in last December, and now there's something called Alpha 0. Okay, so I'll tell you what these variations are. Let's try to understand the why this is interesting. Okay, so games are generally interesting because they're more structured environment. You'd have a very simple simulator you can write simple simulators for games. Okay, because they just have to follow the rules and everything is deterministic. There's no stochasticity here. Okay, all the expectations and stuff vanish. What's complicated is that the number of contexts. So context in such a situation, in a game, is going to be the state of the game. Okay, so here the context is going to be the board state, and so there are too many such board states in this game. A regular game, regular board will have 19 cross 19 size. So here it's not 19, but there will be 19 cross 19 grid size. Okay, so given that there's too many configurations, too many contexts, and so humans have figured out how to play this game. The game is as follows. There are 2 players, a white player and a black player. They both have a bunch of stones, and they place the stones sequentially on this board, and their objective is to capture what is called roughly territory. Okay, so for example, the person playing black stones, if they can put black stones like this, then they get this much territory, and then if the white player has done like this, they have a whole boundary like this, then this is their territory. Okay, and then you just measure whose territory is larger. Okay, and of course in the game you will not let a player do this. Okay, just like tic-tac-toe, you will not let the player do like a straight line, right? Something like that. And you can also, if you surround like these stones, let's say white stones, then that territory is also yours. Okay, the white player has lost his stones. So that's essentially the game: capture territory on a board. Okay, and so before March 2016, a lot of these types of board games were already conquered. Okay, in the sense that, for example, checkers, there's a AI agent which can, level of play, perfect just means, you cannot defeat it at all. And there were other board games for which there were AI agents which are superhuman, can definitely defeat humans. Okay, and there's some RL-based programs which can do that, reinforcement learning-based programs. There are programs, for example, for chess. There are other programs. I don't remember the name of the most recent program, Swordfish or something. So there are programs which can play chess and can beat humans for sure. But there are programs based on reinforcement learning that can also achieve some very good level, okay, than an average player. And Go was the only game which was kind of the level of play by an artificial agent was quite at the amateur level, not even at the professional level. Okay. Okay. So in the game of Go, so what are we trying to do here? So we have this Go, too many states, and because of which we can't, AI agents So because there are too many states, AI agents cannot figure out what's the best thing to do in each situation, in each board situation. Okay, that's the only reason. If there is no stochasticity in the environment, if they had infinite time, maybe try out everything in every situation and figure out what's the best thing to do in each board state. Okay. So actually, we are in the planning setting because we know everything about the rules of the game. So the agent knows the rules of the game. It's just that it's not able to tell in a situation what's the best thing to do. Okay. And so, even though we know the rules of the game, we'll still take a reinforcement learning approach, which is that we're only going to focus on we're not going to focus on planning. We're going to focus on doing something like Q learning. Okay, and we'll see that very soon. Okay. So let's ground something. So what is the problem here? We want to figure out how good is the position S. Okay, S is just a board state. We want to figure out how good the board state is. Then let's define a couple of things. Let's say the reward is 0 for all non-terminal states. Okay, and reward is 1 if let's say black wins, or 0 if white wins. Now a policy is going to be, you're in the current state. A policy is going to be the set of moves for both players. Okay, so the board state is there. Given the board state, if you are the white player, you'll do something. If you are the black player, you'll do something else, right? So a policy is just what would each player do in the current situation. Okay, just think of it as two different policies depending on which side you're playing. Okay. The value function, again, we're going to assign value for every board situation. It's going to be, in some board situations, I'm really destroyed. I can't really recover anything. I'm going to lose. And some board situations are the strongest positions where the opponent cannot really do much to you. Okay, so there's going to be a value assigned to each board situation, and it's just going to be expected reward that you'll get starting from that board state, following a policy pi. Okay, assuming that the black player follows policy pi b and the white player follows policy pi w. Okay, there's no summation here because all the rewards are 0 except for the terminal state. Right? That's only situation when you get a 1 or a 0 reward. That's why there's no summation here. And so this is the value of a state. What is the best value of a state? What is the optimal value of a state? In a sense, you're trying to find the best policy for both the black player and the white player, and it's going to be the best value, the optimal value of a state is going to be find me the pi, which means it's these two guys, which because I said reward is 1 if black wins, so you're going to try to maximize the policy for the black player, and you're going to minimize the policy for the white player. Okay. So this is just a definition of what I mean by optimal value of that state. Okay. In that state, if you're the black player, you're trying to maximize over all policies, over all choices. You want to find the best pi for the worst pi w that the other guy is going to try to do from that state. Okay. There are two players involved. That's another complication here. Okay, so that's that. So we're gonna do so what we'll try to do is find the value of a state. Okay, and we're gonna do that using what is called forward search. Okay, and it's very simple. It's in the sense it's as the name says, all we're gonna do is we'll try to figure out what's the value of the state is, or alternatively we can also figure out what is the best thing to do in the current situation, depending on whether we are white player or black player, by just looking ahead. Okay, what does looking ahead mean? We know the rules of the game. I know if I take action something, if I knew the policy of the other guy, they'll take some action. I know what I'll take. I know what they'll take. So I can actually look at a tree of what all can happen from my current state. If my current state I take some action, the other guy will take some other action, and maybe I lose. Maybe I take some action, he takes something else, I take something else, and so on. So this is basically called the search tree. These are all the possibilities that can happen from this current situation, current board state. Okay. And if I know all the situations, I know at terminals what would happen, right? At terminal either I win or I lose. Okay? So I can attribute, if I could simulate forward everything that can happen in the future, then in each path I know how much reward I'm getting, right? So you can think of intuitively that I can, if let's say in state ST I only have 2 actions for simplicity, then I know exactly if I take the first action, these are all the possibilities. I can somehow average them and get an idea of how good this action is. Okay? If I take this action, these are all the possibilities, and in these I get some rewards. I can look at how much reward I'm getting on average. You can take an average, let's say. And same thing I can do for this side. Okay, take an average. There will be 2 numbers. One of the numbers will be greater than the other, and that's the number that that's the action that I want to take. Okay? And using simulation just means that I can't really do this. From every board situation, I can't really think of every possibility that can happen to eventual ending. Okay? So what I'm going to do is just to sample. I'm going to try some action, look at what the other person does, try some action. Maybe this is the only path that I get to see. That's what I mean by simulate. Simulate what would happen in the future. Because I'm only simulating, I'll see only maybe 1 path or maybe 10 paths if I simulate 10 times. Okay? I'll not see all the possibilities that can happen from that state. Okay? That's what I mean by simulation. Huh? We can't unroll the path as in figure out all the possibilities that can happen and all. That's the whole problem. The number of states is too many. So after every situation, after every state, there are so many actions that the other person can take, given that the branching factor is too high. Okay? You can't really evaluate everything that's going to happen in the future. So that's why you just sample, which means that simulate just means that you try one sequence of paths, sequence of actions, which will lead to essentially one path. Maybe try another set of sequence of actions, will lead to another path. Okay? Yeah. Yeah. The moment you are not exploring, I mean, don't know every outcome, then you are gambling a little bit. Okay. And so that's just to but it's not clear which path to take. Like, how do I go from in the state? What should I do? It's not clear. I said just take a bunch of actions, but that's not interesting. You can just take arbitrary actions, right? What we'll do is use again the notion of Q values to do this forward search in a more interesting way. Okay. So this is a summary of what we could do. So we are at some situation. Okay, ST is fixed. We are in ST is fixed. Let's say we are teeth turn of the game. So the teeth board state, that's fixed. From there, I'm saying just to take a sequence of actions, you'll get to some last situation when you win or lose. Do such simulations, right? I haven't told you how to pick actions, but let's say you did that, such simulations. Then you know how to kind of backtrack back, let's say take a Monte Carlo average and figure out what's the best action to take on each side. And let's say there are only 2 actions, let's say. Okay. We will see today, I'm going to talk about one particular version which is called Monte Carlo tree search, which is going to let you do this, which is going to tell you how to what happened? Escape? Oh, full screen. I'm going to tell you one technique which is called Monte Carlo tree search, and all it's going to do is how to efficiently do these simulations. Okay, I told you. So the context is, I know it's a planning problem because the rules are known. There's no stochasticity, but I can't compute anything because there are too many states. So let me just think of doing what's the best. Think in terms of can I compute at least the best thing to do in a given state. Okay, instead of forget about computing pi, which was from every context, tell me what the best action is. Forget about pi. I'm going to tell you in a given context what's the best thing to do. Okay, and the idea was, okay, in a given context, if I had the resources, I could expand out and figure out in every action that I can take, every action they can take, what all can happen all the way to the end. Maybe the games terminate at every path. Then I can backtrack and kind of take a Monte Carlo average and say, okay, maybe this action is the best because for this action, on an average, I'll always do better. Okay? That was the idea. But now I can't really do that. Can't really simulate to everything that I can take and everything that the other person can do. So I'm gonna say, let me just simulate. Okay, that's a simulation. Simulation just means I just need an access to a rule engine or a game engine. It will tell me, take this action. It will say I'll be new this board state. The other opponent takes some action. I'll be in some other board state and so on. Okay, I'll try very few of those paths, all the possible paths, and based on that, I'll take a decision of what's the best action to take now. Okay, that was what simulation is, and there are a couple of variants of this simulation business. One is simple Monte Carlo search. So this is searching for the best action to take, right? And I have such simulations that I've done. Simple Monte Carlo search will do something, and Monte Carlo tree search will do something different. But both will try to what are both trying to do? Both are trying to find the best action to take. Now, that's why I said simulate because in the game I'm not going to do random things. In the game I'm in a board situation. Now I'm going to think. I'll simulate in my brain what all I can do and what all will happen in a few paths, okay, and then figure out the best action. And then in the real game, I'll actually play one action. Okay, that's also another reason I'm saying simulate. Okay, I'm doing everything in my imagination. Okay, these things I'm doing in my imagination, I guess. Okay, so. So let me actually describe simple Monte Carlo tree search simple Monte Carlo search because it's kind of very intuitive. So let's say a model just means that this is a game of Go, let's say, and I have a policy pi. I need to have a policy pi which will tell me what actions to take in different situations. Okay, it's called a simulation policy. Let's say there's some default policy. Somebody hand engineered saying that this is a board state, do something. This is some other board state, do something. Or it can be as simple as a random policy. In the board state, do whatever random thing you can do. Okay. So what I'm going to do is I need to know. My goal is to find the best action to do now. So what I'm going to do is right now I'm in some board state ST. For every action A that I can take, I'll take that action, and then I'm just going to employ my simulation policy. Maybe it's a random policy which says do random. Employ my simulation policy, get to some terminal state, which means that I won or lost. Do k of them. Okay, repeat this k times in my mind because I'm not in reality going to do anything yet. Do this k of times, and then I'm just going to define q of s comma st comma a as just the average of all the rewards that I get. Okay, average of taking this action. How many times did what are the rewards that I got? ST A, I did this k times, so average of k times the total reward that I got. And game of Go, the only reward is at the end, so you just look at whether I won or lost, essentially. In this state, taking some action, I won or lost. Proportion of times I won or lost. Okay. And then this is very intuitive, right? Once I know for every action, the proportion of times I win, then I'm going to take that action which will be the one which corresponds to the highest proportion of wins. That's what this is. I found q of s comma a for every a. I'm just taking that action which has the highest q value, and this is actually a q value because it's essentially the definition of q value. Right? Q is saying q state action value function is just essentially saying in this state take an action and follow some policy. Ideally, it should be q pi of s comma a, but right, that's by definition q value function. So this is called Monte Carlo. This is called Monte Carlo search, simple Monte Carlo search. Okay. Any questions at this point? there may in the current board situation, I may have few actions to take. I may have few actions that are possible. For each action, I'm saying do the simulation k times. So maybe there are 10 actions I can take. For each of the 10 actions, I'll pick some parameter k, 100. For each action, I'll do 100 simulations. I need to have a simulation policy, which could be random, for example. 100 times I'll roll out and figure out what's the average, how many times I'm winning from there. But I'm winning is basically focused, is dependent on the simulation policy, but I'll just look at proportion of times I'm winning there. Same thing with each action and get these numbers and take that action which has the highest number. Of course, this depends on knowing, having some simulation policy.
How is having high simulation policy different from having that huge matrix that you can handle?
Simulation policy is just the huge matrix would have to say for every state, for every action, what is the number. Pi is saying in this state, what should I do? Okay. Simulation policy is not encoded as like a vector. For every state, what is the action? It's not encoded that way. Simulation policy, think of it as like one example simulation policy is do anything at random, whatever you can. Like in a board state, there may be some free spaces where you can place the next stone, place it at random. I don't need a huge memory, a huge anything to do that. But maintaining a table is very difficult. And in fact, maintaining a table is difficult. So that's why we narrowed down the problem to saying, just tell me what's the best action state at just the given state only. Don't tell me what Q star is, which is the whole table. Or don't maintain the whole table. Just tell me one row of the table, essentially. This is easy. This is really easy to handle because number of actions can be maybe 10 or 20 or 100 or whatever. That's easier thing to handle.
Professor, I have regarding simulation. So there could be even for k primes, there could be various searches, right? So how do you
Not various searches, various paths.
various paths. So you can say all the paths?
Yeah, that's what we were averaging, right? I could have gone to SP different paths, right? Like in each run, in each execution or each simulation, I would have potentially hit different states, did something different, very different, and so on. Ultimately, reached some terminal state. So I'm just taking the average of them.
Those paths will say.
Yeah, there are different paths, but ultimately, yeah, there may be different paths. Yes.
No. For the next time we run it, are we going to do it?
Next time, as in you're taking next simulation. Yeah, it will be different paths. And we'll have a GT, right? Remember, GT was the total return. It was defined in the last lecture, but think of GT as this sum of rewards. That's what it is. Yeah, it can be different paths, but we are just taking the average. In the board game, for example, all the intermediate rewards are actually 0, except for the last reward, and that's 1 if you win, 0 if you lose. So essentially, it's saying the proportion of wins that you have if you take action A and follow the simulation policy.
So in a particular position, we will simulate, right?
Yeah.
So what will be the different types of simulate? Like, if it's for
Simulation just means execute a policy. So in every state, pi will tell you what to do for both the players actually. Remember, pi was the tuple of pi subscript b and pi subscript w. So it will tell you what to do for both players. So that's how you would unroll mentally. It's all in your imagination because you want to just figure out what is the best thing to do now in the real world. But you have some computation, but you have a simulator essentially, which will tell you what's going to happen in the future. So you will simulate and see what's the best action to take, and then you actually take in the real life what action. That's what most of the softwares will do in these types of board games. Example, they'll have access to a simulator. In reinforcement learning, that's what it is. You have access to reinforcement learning will compute the whole Q table. That's the slight difference here. Here we can't do that. So you're saying in each situation, just hallucinate, try and simulate and figure out what's the best thing to take, best action to take, and take that action. It is hallucination because you have a model of what is the real life. Okay, in the board game case, it's the same. You know exactly the rules, but in real life, you'll have to have a hallucination because you have to have a model of the reality, or which you will run simulations and figure out what's the best action to take and then take that action. Any other questions? Okay. I see that I don't have time to talk about Monte Carlo tree search, which was the most interesting. So Monte Carlo tree search is the algorithm used in AlphaGo and all the other versions, AlphaGo 0 and Alpha 0. Yeah, so actually I should have said this. So in a current position, you just use the simulation policy, roll out all the way to the end. You lost here, here. Yeah, here there's some reward, here there's some reward, and then just go back and attribute that to each of the actions and take that action, which is the highest one. Okay. So let me skip Monte Carlo tree search because we don't have time at all. Okay, so because I skipped Monte Carlo tree search, I'm gonna describe not what was the engineering trick in AlphaGo, but I'm gonna describe the tricks which are actually also true for the simulation procedure I just told you, okay, which is as follows. I told you there is a simulation policy which will tell you, in every board state what you need to do next. That was the input to the simulation, simple Monte Carlo search. Instead of that, you can create what is called, not instead of that, to define a simulation policy, I'm going to define a policy which is going to be a policy network, okay? Which means it's going to be a neural network. And what is the neural network going to do? Its input is a board state. Okay, that's what a simulation policy is. Given a board state, take the next action. So, policy network is going to take a board state and it's going to tell the next action. And next action is going to be actually where to place the next stone. Okay, I mean there probably is one more action which is pass or something, but anyway, so think of a policy network as a mapping from a board state to what to do next. And what to do next, they're going to capture it as a PMF. It's going to say place a stone here with high probability, place a stone here with high probability, place a stone here potentially with high probability, and everywhere else don't place a stone. So that's what a policy has to say. Given the board state, where to place the stone next, right? That's what that's a policy. Policy network just means that this mapping from a board state to a distribution or where to place the stone next. 19 cross 19 locations are there. So think of a PMF on this 19 cross 19 locations, which is like a square, which is telling you where to place next. And this mapping from here to here is a neural network. Okay. So that's an example simulation policy. I mean, AlphaGo 0 has some other details. Let's not worry about AlphaGo 0. In simple Monte Carlo search, you have a simulation policy. Think of potentially a network, neural network, telling you where to go next. Okay, and so think of a neural network. But how do I get its weights? So what in AlphaGo 0 they do is they look at human games. So in human games means human games are logged, which means that it's like this is the board snapshot, this is the first player who did this, there's the next player who did this, there's the next player who did this, there's the next player who did this, there's the whole data like that. So that's essentially your supervised learning data, which is like given the board state, this is the action the human took. Can you build a network which will tell me, which will predict what the human took? So what the human took is your label data. Given the board state, what the human did is your label data, and this neural network is basically predicting what the human took in that training data, and then you can use that as a simulation policy. Okay. I mean, in simple Monte Carlo search. Although here AlphaGo does something else slightly different, but that's the network here. Second trick, okay, is that if I want to do simple Monte Carlo search, I'm in a state. I use that policy network, figure out an action, take that action. Opponent also, opponent's kind of symmetric, so they'll also use the same network essentially. Take another action, and then we land into a new state, take another action, and so on. Should we really have to continue all the way to the end of the board? Okay. So instead of that, there's another neural network that we introduce, which is that given a board state, it will tell you what is the value of that state. So what is meant by, remember, board state is a context. V of s, value function, is just saying how valuable that state is. Okay. So V of s is supposed to tell you from that state, if you do something interesting, as in if you do something, take right actions, what is the expected reward you get, right? That was the definition of value function. So people in AlphaGo, they've also created another neural network, but just a function, which is like given a board state, it will tell you how important that state is. Okay. How do we learn this value function? That's slightly more trickier, because for that you really need to know, need to have example data where there's a board state, some games happen, and ultimately you got reward or not. I mean, you won or not. If you have such data, where starting from board state, you won or not, using that training data, you can learn a network, a function, which will predict what the value of that board state is. Okay. So, if you have a value network, then you don't have to do the simulation unrolling. You don't have to do the simulation all the way to terminal state. So what you do is, given the ST, you take this. It will tell you what the next action is. You take that action. The black player, let's say, will also look at the state, apply this, and take the next action. Okay. Maybe you do that twice or thrice. You'll reach to some state. Then just put that as input to this guy. It'll tell you what the value of the network is. Value of that state is. That's it. You're not unrolling all the way to the end. You stop that unrolling. Okay. So you're not really unrolling. This actually is compressing the whole unrolling procedure and saying in this state there is this is the only value of that state. Okay. So you don't have to really go all the way to the end to figure out what the value of that what the values are. All the rewards are. It's just telling you this simple number that you can just use. Okay. So those are the two tricks that they use to manage this really large state space problem. That's the only issue with Go or many of these board games. So the number of states is too many. That's why you can't really try out everything. For tic-tac-toe, the number of states is about 30,000. It is a large number, but it's not large enough. So for tic-tac-toe, you can always write a agent which can actually try everything, do everything, figure out what's the best thing to do now. Okay. But in these games, you can't really do that. And so these are the tricks that they use. Yeah, so it's a supervised learning problem here, where where what they do is they just start with the board position, and what they do is actually just employ a policy network on both sides and make the policy networks play games, and ultimately just end somewhere, and that's your training data. Okay. Yeah, I mean ideally value network. If you want to train the value network, you actually need to explore everything, but they just do supervised learning here, which is essentially that from a starting board state, employ the policy network against itself, keep playing against itself, essentially, which means that given a state, it will tell you what action to take that action again from a new state, take the policy network to say what the next action is for the other player, take that action and so on, keep doing that, you'll end somewhere. And that will be either somebody wins or somebody loses. You remember that, whether you won or lost from this state. And you have training data now, which is supervised learning data. These are the labels, won or lost, and the board state is your input feature. So you have a supervised learning problem, just solve the, minimize mean square error. I mean, it's actually a complicated problem, but find the weight of this neural network. Okay, so just to wrap up. So reinforcement learning is a great framework to make these softwares data driven. They are not rule driven. No programmer is writing in this situation do this situation do this. Okay, it's all data driven. Because it's data driven, ideally you need to have access to simulators, unless you want to try different things in real life and lose money and so on, right? That's the one thing. You only have to just specify what the goal is, collect as much reward as possible, and you only have to give feedback. Okay, oh, you're doing something correct, you're doing something wrong. In the games, ultimately what it does, it only gets feedback whether it won or lost. Right? You don't have to give intermediate rewards. You can give intermediate rewards. I mean, they can help. They won't hurt. Function approximation lets us manage scale, going from like a 2D grid world to actually a camera-based thing, functional approximation is what will get you there. Okay? Designing agents which can work with really large, context measurements like images and so on. And it complements deep learning in the sense that deep learning solves just a perception problem. Perception problem means essentially classification regression. I mean, not all of deep learning, but majority of deep learning is like that, right? It just solves a perception problem. What are you seeing? What are you measuring? Okay, you're seeing a cat, you're seeing a road, you're seeing the pathway, you're seeing a pedestrian, right? And reinforcement learning, or MDPs, or bandits and contextual bandits, they're solving the decision-making problem, planning problem. Okay, they're saying, tell me what your perception is. Okay, maybe perception will tell you what forecast can happen, what can happen in the future. But given what can happen in the future, you have to take the best decision, right? That's what these set of techniques are solving. Okay, like the 3 such thing that we said. What is the best action to take given forecast of the future? Essentially, the simulations are forecast of the future, whether you will not lose, right? There are a lot of things which are still not fixed. So there's renewed interest in reinforcement learning because of these latest improvements from DeepMind and other groups. So I had a video for this. I think we've seen it too many times. So that's roughly closes the 3 lectures on decision making. That's it.